We start this lecture with an overview, a plan for what will be presented. In this pre-lecture, we will focus on statics, the study of forces on objects that do not move. We will start by looking at the torque produced by the weight of a solid object, and will find that it can be calculated by simply assuming that the entire mass of the object is located at its center of mass. We will then move on to determine the general conditions that must be satisfied for a system to be in static equilibrium. First, the sum of all the forces acting on the system must be zero. Second, the sum of the torques produced by the forces acting on the system must also be equal to zero. We will close by applying these conditions to a few specific examples. Up to this point, we have considered the torque due to forces whose point of application was clear. The tension in a string wrapped around a cylinder provides a force acting at the edge of the cylinder, as does the force of friction acting on a ball rolling down a ramp. We now want to consider torques due to continuous mass distributions. We will show that the torque produced by the weight of a solid object can be calculated by simply assuming that the entire mass of the object is located at its center of mass. Here we see a thin beam attached at one end to a wall by a hinge. The hinge can rotate freely, so when the beam is released, it will start to swing downward as shown. Clearly, the gravitational force is producing the torque about the rotation axis defined by the hinge. To calculate this torque, we need to integrate the contributions due to all of the mass elements dm along the length of the beam around this axis. Each mass element will produce a torque into the screen so that all we need to do is to set up an integral to determine the magnitude of the torque. After taking the constant terms outside the integral, we are left with the integral of r dm. Now, this integral is exactly the integral that is needed to determine the position of the center of mass. Therefore, we can replace the integral in our expression for the magnitude of the torque by the distance from the hinge to the center of mass. The resulting expression for the magnitude of the torque is, as promised, just equal to what we would obtain for a point particle located at the center of mass of the beam, and whose mass is equal to the mass of the beam. This result is completely general and is true for any shape. We chose a thin beam for this example just to simplify the calculation. In the last slide, we found that the torque on a solid object about some rotation axis due to gravity can be found by assuming that the weight of the object acts at the center of mass of the object. We will now examine this result in more detail to obtain an alternate expression for the torque. From the definition of the cross product, we know that the magnitude of the torque can be found by multiplying the magnitude of the vector from the rotation axis to the center of mass of the object times the magnitude of the weight times the sine of the angle between them. Since the weight always points down, the product of RCM and the sine of this angle will always be equal to the horizontal displacement of the center of mass from the rotation axis. In other words, the magnitude of the torque on some object due to gravity about any rotation axis is just the weight of the object times the horizontal distance that the center of mass is displaced from a vertical line through the axis. This result makes sense. For example, the torque due to gravity will be zero if the center of mass is directly below the axis. The object will just hang there without moving. This result also implies that the torque is biggest when the object is rotated so that the center of mass is at the same vertical height as the axis, making the sine of the angle between RCM and the weight its maximum value of 1. It's important to note that the torque will always have the form we see here. It can always be expressed as a product of a force and the perpendicular distance of a line through this force and the rotation axis. This perpendicular distance is called the lever arm. In the case of gravity, we see that the lever arm is just the horizontal displacement of the center of mass from the rotation axis. In general, the lever arm does not have to be horizontal, but it will always be perpendicular to the force. On the next slide, we will do an example that illustrates this calculation. Here we see a horizontal beam having a mass m and length L attached to a vertical wall by a hinge. The far end of the beam is supported by a massless wire that makes an angle theta with the beam. Our job is to determine the tension in this wire. We begin by drawing and labeling all forces acting on the beam. The weight acts at the center of mass, and the tension due to the wire acts at the end of the beam in the direction of the wire. There is also a third force, due to the hinge, which supports the beam at the wall. We will allow this force to have both x and y components. Since the system is static, both the acceleration of the center of mass and the angular acceleration about any rotation axis must be zero. Since the acceleration of the center of mass of the beam is zero, the total force on the beam must be zero in both the x and y directions. Therefore, we can write down two equations that must be true. These two equations alone do not allow us to solve for the tension in the string, since there are three unknowns: the tension and both components of the force due to the hinge. The good news is that we can get another equation by realizing that the angular acceleration of the beam about any axis is zero, which means that the torque about any axis must also be zero. We now want to choose an axis of rotation for the calculation of the torque that simplifies our calculation. Since our task is just to find the tension in the wire, we can pick a rotation axis perpendicular to the screen that passes through the hinge. We see immediately that the lever arm of the force due to the hinge is zero about this axis, so the torque due to this force about this axis is also zero. What about the torques due to the other forces? The magnitude of the torque due to the weight of the beam is just equal to the weight times its lever arm. Using the right-hand rule, we see that the direction of this torque is into the screen. The magnitude of the torque due to the wire is equal to the tension of the wire times its lever arm. Using the right-hand rule, we see that the direction of this torque is out of the screen. Therefore, the two torques are in opposite directions so that we assign them opposite signs. We can solve the resulting equation to find a simple relationship between the tension in the wire, the weight of the beam, and the angle of the wire. We can now determine the force the hinge exerts on the beam by solving our two original equations we found using Newton's second law after substituting in our newly found value for the tension in the wire. We will now change the geometry of our beam and wire example and determine the force at the hinge as well as the tension in the wire. Now, once again, we start by writing down Newton's second law for both the x and y components. We can immediately solve the y equation for f sub y. The x equation, though, contains two unknowns: the tension and the x component of the force exerted by the hinge. To solve for these two unknowns, we need to write down the torque equation. We again pick a rotation axis through the hinge, making the torque due to the force of the hinge zero. The magnitude of the torque due to the weight of the beam is equal to the weight times its lever arm. Using the right-hand rule, we see that the direction of this torque is into the screen. The magnitude of the torque due to the wire is equal to the tension times its lever arm. Using the right-hand rule, we see that the direction of this torque is out of the screen. The two torques are once again in opposite directions so that we assign them opposite signs. We can solve the resulting equation to find a simple relationship between the tension in the wire, the weight of the beam, and the angle of the wire. If we now return to the Newton's second law equations, we see that the magnitude of its x component is equal to the tension, and the magnitude of its y component is equal to the weight of the beam. The procedure we have demonstrated in these last two examples will work well for any statics problem. Namely, start by drawing a picture that shows all forces and where they act. Using this picture, you can write down equations that determine that the translational and angular accelerations are zero. You are free to choose a rotation axis that simplifies the calculation of the torques. We will close this pre-lecture by considering what happens when the wire in the previous example breaks. What is the angular acceleration of the beam as it falls? Here we see the string break and the beam rotates about the hinge. This motion is a pure rotation, whose angular acceleration can be determined using the torque equation. Since the wire is no longer attached to the beam, the only torque around this rotation axis is that due to gravity. On the last slide, we determined both the magnitude and the direction of this torque. We can therefore determine the magnitude of the angular acceleration by simply dividing this torque by the moment of inertia of the beam around the rotation axis. Previously, we determined that the moment of inertia of a beam about its end is equal to 1/3 its mass times the square of its length. The first thing to note about our result is that the angular acceleration is not constant. It depends on the angle theta. It is biggest when the beam is horizontal and smallest when it is vertical. Of course, the angular displacement and the angular acceleration are not independent variables. If we write alpha in terms of the second derivative of theta with respect to time, we obtain a differential equation. This equation is difficult to solve analytically, but we can, and we will, solve it in the small angle approximation in a few pre-lectures when we discuss simple harmonic motion. We conclude with a brief discussion of the main points of this pre-lecture. First, we determined that the torque produced by the weight of a solid object can be calculated by simply assuming that the entire mass of the object is located at its center of mass. Second, we found an alternate expression for the magnitude of any torque as simply the product of the force and its lever arm, the perpendicular distance of a line through this force and the rotation axis. Third, we investigated the conditions for static equilibrium and applied them to a few specific examples. In particular, we observed that for a system to be in static equilibrium, the acceleration of the center of mass and the angular acceleration about any rotation axis must be zero. Consequently, the requirements for a system to be in static equilibrium are: 1. The sum of all the forces acting on the system must be zero, and 2. The sum of all the torques produced by these forces must also be zero.